Can we color a 17 by 17 grid with only 4 colors so that no rectangle ever has its 4 corners the same color? For years, nobody could show that such a coloring exists. In 2012, a team finally found one after about 7 hours of computation. In this video, we reproduce their approach on a laptop. That same search now takes about a minute. The 2012 approach runs on top of a tool called a state solver for satisfiability. You give the solver a pile of Boolean variables called x1, x2, and so on. Each is either true or false. Those variables appear in clauses. A clause is a disjunction, one variable or another, possibly negated. The whole formula is the conjunction of clauses. Every clause has to be true at the same time. Here is a 3-variable example. One assignment of trues and falses satisfies all 3 clauses. The solver's job is to find such an assignment or to prove none exists. That description sounds almost too simple to be useful. It is not. SAT solvers have been sharpened for about half a century. The modern ones chew through millions of variables and billions of clauses. They verify chip designs, plan logistics, break cryptographic puzzles, and crack combinatorial questions that nothing else can touch. Solver engineering is still a live research area. Back to the grid. To send it to a SAT solver, we need to encode the rule as Boolean variables and clauses. Make one variable per cell color pair. If the variable for row R, column C, color K is true, that cell has color K. Exactly one such variable is true for each cell. Then the forbidden combinations are every monochrome rectangle. For every rectangle and every color, the 4 corners cannot all share that color. Millions of tiny clauses, all mechanical. So with the direct encoding, 15 is fine, 16 already stalls, and 17 is out of reach. We need a different approach. The first move is counterintuitive. Target 18 by 18 instead of 17. Yes, it is 1 row and 1 column larger, but 18 is even, and in the next scene you will see why that matters. And any rectangle-free 4 coloring of 18 by 18 gives us 17 by 17 for free. Every 17 by 17 subgrid inherits the property, because removing a row and a column cannot create new rectangles. Instead of coloring every cell of the 18 by 18 grid with one of 4 colors, we only search for the cells of color 1. That is 81 cells, 1/4 of the grid. Call that set W. We ask 2 things of W. First, W itself must be rectangle-free. No 4 cells of W at the corners of any rectangle. Second, W must be disjoint from its 90, 180, and 270-degree rotations. Then those 4 rotated copies exactly partition the board, 1 color per rotation, and the whole coloring is forced by W alone. I ran this on a laptop. In about a minute, the solver returned a valid W. Here it is, 81 cells scattered across the 18 by 18 grid. Now rotate the set 90 degrees. Every cell lands somewhere new, and we paint those cells the second color. Rotate again for the third, once more for the fourth. Every cell of the board now carries exactly 1 color. And because rotation preserves rectangles, the rectangle-free property of W passes to every color class. Peel off any row and any column, and you have a rectangle-free 4 coloring of a 17 by 17 grid. Why did the 2012 team need 7 hours, while a laptop today does it in about a minute? The short answer is Moore's law. Moore's law is the observation that computer speed roughly doubles every 18 months. Over 14 years, that's about 9 doublings, a factor of 500. 7 hours divided by 500 is close to 50 seconds, very close to what a modern laptop measures. So the hardware almost did it on its own. The 2012 team also used sharper techniques on top of the basic rotational search, which is why their runtime was hours, and hours is minutes, not seconds. This rotational trick is one reformulation. For a SAT solver, how you encode a problem can change the runtime by orders of magnitude. Choosing encodings well is an active field with its own heuristics and benchmarks. The 17 by 17 conjecture did not fall to brute force. It fell because someone asked the solver for the right thing.